Hi, I'm Kiko Galvez. I'm from Colgate University, and the purpose of this video is to show you how to set up and conduct experiments with single photons. More specifically, I'm going to show you the setup and all the alignments that are needed to do to set up the apparatus for doing parametric down conversion. The apparatus is right here in front of me, and it needs an optical breadboard of about 2 by 5 feet in dimensions, and as you can see, not many optical elements, and I'll describe each of them. And in addition, we need a computer for collecting the data, and we'll get into that later as well. Let me just show you a little bit about, in general terms, and later on we'll go more specifically. The first component is the laser that eventually produces photon pairs. In this case, we have a laser pointer that we're going to use, and we could use other conventional lasers. I've used this one, say, in the past. And okay, then the light is gonna of the pump laser is gonna be incident on this crystal, and later we'll align it. But this will produce pairs of photons. Then the pairs will travel over here, and then here, in combination with multimode optical fibers, we collect the pairs, which eventually come to detectors, single photon detectors, and then the signals from the detectors then go to the computer, and there we can take data and perform the experiments. So this is really the basic setup. Now, in addition to that, we have some other alignment tools. We need a collimator. We also need a plumb bob, and you will see me using it as well. It is very important to have that. And okay, now in order to complete that alignment, we use an additional laser. In this case, I'm using a very simple and convenient laser. It's a fiber laser. But one could use also a conventional helium neon laser, something such as this, and then we would put this instead here, and then we could do the alignments with this laser as well. But at this point, this is actually quite convenient. And these fiber lasers normally come as a module, and then we have to provide, in addition, a single mode fiber and a collimator. What's here? So in order to see what this arrangement actually means, we should go to a board so I can explain the general schematic of the apparatus. Okay, so here in this board, I have a schematic of the apparatus. And eventually we want a beam from the pump laser, which is blue, in particular is 405 nanometers, and it's going to be incident on a crystal that would go right here. And of the crystal, we're going to have photon pairs coming at angles. And we're going to make our design so that the photons that we're looking at come at plus and minus 3 degrees. But there's no reason why it can be 4 degrees or less. It's just a convenient arrangement. Now, I set it up this way so that this particular beam of down-converted photons is horizontal. Let's say it's parallel to the holes on the breadboard, and there are reasons for that. So again, the setup is pump beam comes to here, and photon pairs come out in these directions. the photons are from down conversion are very weak, so we can't see them. If we put a card, we just can't see them. The wavelength is also in the near infrared, so even if it was intense enough, it would still be hard to see them. And so we're basically working in the dark, and so we need some help for aligning the optics. So for that reason, we use an alignment laser. And so then what we are going to do is we're going to set up the laser so that it comes here, hits a mirror, hits another mirror, and then this mirror is going to go straight through the crystal, which I'll put here, and then again go straight parallel to the holes on that breadboard. And now, so this laser beam is going to mimic the path of this beam of down-converted photons. We will also put another mirror here that we will flip in and out so that we could mimic the trajectory of the other photon pairs that come in this direction. Once we've done that, then we need to send the pump beam after a mirror, and because these two are already set up, normally we set this up in a linear stage, and you'll see that. So then this beam comes through here, passes through the crystal right where these two beams would indeed cross, and then go right through here. Okay, so the first thing we're going to do on the table is make markings of where we want to have the different components, and then we need to know what are the best tricks to align the light and the beams so that we are indeed at plus or minus 3 degrees from the pump beam. Okay, so now we will go back to the table. Okay, we're back. So before I start doing everything, there's one little detail that we need to keep track of, and that is that the light has to be all at the same level over the table. So then we need to set up a height. The crystal has to be at a certain height, and then the laser has to be at the same height as well. The alignment laser also has to be at the same height. This is. And then the collimators, it is helpful to have your hardware set up so that they are also at the same height. So everything is at the same height. Okay, I'm going to take these out of here. Our first alignment is going to be to send the beam in this direction. So we turn the corner here with the mirror, and this mirror is mounted in one of these pedestal mounts. I like the pedestal mounts because they're very stable. So then the light is going to go turn this corner and then turn another corner and go the length of the table. So then I'm going to show you how to do this alignment. It's critical because the more alignment precision that we have, the easier it's going to be to do the experiments. So the first thing is I'm going to show you a method that we use, and that is to use an iris and a couple of, four knobs or screws put along the holes in the table so that we can make sure that the light from the laser is parallel to the holes on the table. So this is our laser. So I'm going to turn it on. I'm going to put this down here. Okay, we have a laser beam here. It is 1 milliwatt in power, so it's safe. So I don't have to wear goggles right now. And then the first thing that I do is I make some crude alignment. An easy one is to to see that the beam goes on top of the holes. That's a good starting point. And I clamp this. The next step is to have the light go through an iris. If the light is going parallel to the holes in the table, then if I merely displace the iris from a near position to a far position, the beam will go. And if the beam goes through the iris in the front position, it'll go through the iris in the back position. But if it doesn't, then we need to do some alignment. And so the alignment is the following. In the near position, we have to adjust the position of the iris. Make sure that it goes through the iris, and as it is doing right now. And so then I move it to the far position. In the far position, it is off. So then when it's in the far position, I tilt the mount of this laser. Actually, the laser is in here. The light is channeled through a single mode fiber to a collimator that is mounted on a mirror mount. So then I move the mirror mount. Make sure this thing is nice and clamped. I move the mirror mount so that the light goes through the iris. Then, since I steer the beam, now it's not going to go through the iris in the near position. So then, now here, I don't steer this because otherwise we'll go back to where we started, but I will move the iris. And, okay, so I clamp here. All right, it goes through the iris, and then I go to the back position, and it's off, but not off as much as before. So I adjust it again. In other words, this system of alignment converges. So we go back one more time, and now we're really close. So we adjust this one here. And then we go to the far side, and the beam is almost there, and I'm sure this is the last step. Okay, I made sure the light goes through the iris. Now when we're in the near position, it's hard to tell. And at that point we could say it's good enough. So then now we have a beam going from here to there, and it's going parallel to the holes on the table. The next step is to now put a mirror and make it turn the corner. And that's what I'm going to do now. So I'm going to block the beam. Let's do that. Then I'll put the mirror where I think it should be. Okay, and it is crudely aligned to turn by 90 degrees. So then I'm going to clamp this mirror, and I use the clamps that are sold for it. And now I want this beam to also be parallel to the holes on the table in this direction. Now, I did some pre-alignment in the vertical direction. So the vertical direction is fine. So we need to do an alignment in this direction. So we do the same thing. Okay, so what I've done is I've already done the alignment for this beam. So this beam right now turns this corner by 90 degrees, and now turns this corner, but I haven't aligned this side, just so I show it again. And so this mirror is not fully aligned. So I'm going to put my iris downstream, and the beam is not even close. So I'm going to steer, again, in the far position, I steer the mirror, in this case. So the irises are dark, so sometimes with a little less light it is this much easier, but it's okay. All right, so now I move to the near position, and we're a little bit off as it is expected, so I'm going to move the iris. Now I go to the far position, and we just less off. And vertically we are fine, because once we've aligned vertically on the first leg, the iris is already at the right height, so we don't need to do much more vertically. But sometimes things get bumped, so it doesn't always happen the same way. Okay, this thing is almost there. All right, so now we have the light following that path of one of the down-converted photon beams. So then now we need to set up our the place where the crystal should go. And normally we want to have it early on the table, probably the first quarter or so of the table, so that the beam has time to spread out. We don't want to make it too close to here, so that the mirrors that are used to send the light through the paths run into each other. So I would say this is a good spot to get started. So the next step is I'm going to define the place where I want the crystal to be, and will be approximately right here. And okay, so I'm going to put the iris. Okay, what I have here is a plumb bob. Okay, it is made out of brass. A dark nylon thread. Brass is important because it is non-magnetic. These tables are magnetic, so if you use a needle, no luck with that. So you may want to have your shop person or a talented machinist put together one of those. Okay, so now if you can see the thread is casting a shadow on the paper, a shadow of the beam, and it splits it pretty much into two halves. So I'm going to make my first mark, which is where I want the crystal to be. I'm going to put it right there. This piece of paper will help us see the points on the table, and then I use a pencil. And we're pretty close. All right. Okay, so that's our starting point. Now, from here we need to define the direction that is 3 degrees from this one, and also 3 degrees further from this one. And so the next step is to use a ruler. And so we use this ruler. And I always pick 1 meter because it's a nice round number. So I'm going to make a mark down here, right where the beam goes, and that it is 1 meter away from the position of the crystal. Okay. And then I'm going to make a mark here. And I prepare these sticky tapes. Okay, so the tip of that piece of paper marks 1 meter downstream from the place where we want our crystal. Okay, now plus 3 degrees, 1 meter away, corresponds to a distance of 5.2 centimeters. So that's what we're going to do here. We're going to mark 5.2 centimeters. So that'll be 10.4. I make 2 pencil marks, but pencil doesn't paint well on the table, so I'm going to put these marks with a sticky paper. Okay, so those points are 5.2 centimeters apart. So the next step is to set up a second beam that now goes to this position. Okay, the beam is now going there. And we're going to use a flipper mirror. We need a flipper mirror because we need to intercept the beam before it hits this mirror. And at some point, we want to go back to that other one in case we want to do alignment. So we need a mirror that we can put on and off. And then this one is very convenient. It's called the flipper mirror. They sell it in New Focus. Nowadays, Newport Corporation. Okay, so then what I'm going to do next is make sure that the beam goes through this point and through this far point. Now, since I know the points here and here, I could put irises, one here and another iris here, and make sure that the beam goes through those 2 points. Okay, so I have already done the following alignment. Put the flipper mirror here, make it go through the iris, and then I put the iris exactly over the place where we want to put the crystal, and I did that with the making sure that the plumb bob cast wire thread caused a shadow. And then once the iris was in the right place, I put the my plumb bob here and very painfully aligned this mirror. This is a bit of a critical alignment because the positioning of the mirror is important and is very coarse, but we did it. Okay, so now the next step is to send the blue laser so that it goes through here and now hits the middle point here. And so that then we would have the red at plus or minus 3 degrees from the blue. So I'm going to bring over our laser pointer, which will go somewhere here. And then we need a mirror that redirects the laser beam through the iris and to where it should be. Now the flipper mirror is going to be in the way, so I'm going to lower this down and now do the same process. I have pre-aligned the blue laser so that it is coming out horizontal on the table. Okay, so I just finished aligning the blue laser. It gets the beam gets reflected of this mirror, which is in a mirror mount. So in this case, we have a lot of freedom because we can move the position of the mirror and its orientation. So it could meet the following criteria. It goes through the crystal specified by the iris, and it comes here to the position where it would cast a shadow at the midpoint between the two down-converted beams, plus or minus 3 degrees from them. So we've done that. So the next step is now to start working on putting collimators and other things. Okay, so now we have everything aligned. So what I'm going to do is bring the crystal now, and then here it is, and I'm going to put it in the way. But before I do so, I must say that these crystals are absorb water vapor. So normally I have them in an urn like this with desiccant. So normally I put the urn here, and then when I do the experiment, the crystal gets put in the right place, and then we clamp these two ends, and so then the crystal stays permanently in the setup. Right now I don't have to do that, so I'm going to use the crystal directly. And of course, when we're done using the crystal, we put the urn, and it has desiccant in there, so then the crystal is happy. So now I'm going to remove this. I'm going to block the beam. Take the iris off, and then put one of the problems of the safety glasses is then you can't see the beam. So I just want to make sure that the beam is going whole through the crystal. And the crystal is on top of that point. I think this is the spot. And then I look at the reflection of the face of the crystal so that I can align the crystal. Normally the crystals are cut so that it produces down-converted photons at the right angles when this crystal is perpendicular to the incoming beam. So I look at the reflection of the front surface of the crystal so that it goes back into the beam, and then we know it's perpendicular. Okay, that looks okay. So I'm gonna have a mount here. Mount clamp, and I'm going to make sure I didn't move the crystal. I did. So for now we're done with the blue laser. We're going to use the two alignment lasers, and so we're going to start with the one that goes straight through here. I turn the alignment laser on. Then I make sure that it indeed goes to the crystal, which it does. So the crystal really is at the intersection point of that red beam and the blue beam, which is what we want. Probably I'll, at this point, since I'm not going to use the blue laser, I'm going to turn it off. I can take my glasses off. Okay, so the next step is going to be to put the collimators that collect the light and send it to the detectors. Now, it is possible that when we aligned the beams with this plumb bob, it's a crude method, has an uncertainty of about half a millimeter. It could well be that these points aren't exactly where they should be. So we have to allow for some adjustment. But now if I put the collimator, and once the collimators are aligned, I move it, then the alignment of the collimator gets ruined. So we have a piece that we have here that has a radius of curvature of 1 meter. So if I put it right where the marks are, which is that it forms an arc of 1 meter radius with the center of being the place where the crystal is, then if we translate the collimators along this track, and if they were aligned to be looking at the crystal, then as I translate this, they will continue to look at the crystal, which is what we want. So now I'm going to clamp this. So the next step will involve positioning the collimator. And we're going to use this collimator here. This positioning of the collimator is the one that gives the most trouble to people. That is because non-converted photons actually come in a cone, and we're going to grab the ones that are at a certain height. So this has to be at the right height. The cone is plus or minus 3 degrees, so it has to be the right position. And then finally, the collimator has a set of lenses that focus the light onto a multimode fiber, one of these, that we'll use in a minute, and it has a very small aperture, so that the combination of collimator and fiber accept a very small solid angle. In other words, the collimator has to be looking straight at the crystal. So the alignment of the collimator involves 6 degrees of freedom, 2 that have to do with the actual position in the XY plane, and 2 others on the actual inclination of the collimator as it looks into the crystal. So the first thing that we do is we're going to use the lens of the collimator to align that collimator. We're going to do that the following way. The beam is now going straight onto that card. I'm going to put a different card, and this card will go here, and I set it up so that I put a mark, and the beam is hitting straight on to that mark. If the collimator is at the right place and looking straight at the beam, then after the collimator, the light is going to expand, and if it is aligned, it'll expand on a circle that is concentric with that mark. If that is not the case, then the expansion of the beam will occur off the, not centered on the dot. So I'm going to move this. And so right now what I see is an expanded beam, but the expanded beam is a little high from the dot. That is, it's not centered. So what I'm going to do is I'm going to move the position of the collimator so that expanded beam is centered on the dot. Right now it is centered on the dot. Okay, now the next step is that this collimator has to be looking to the crystal. This collimator has a mount that has been nicely machined so that if I put a mirror on the face of that collimator, it's going to be perpendicular to the axis of that lens and the axis of the collimator. So if I put this mirror flush with the front surface of the collimator, the beam, if the collimator is looking at the crystal, the beam will go straight back to the crystal. Now, so if I put this thing here, the beam is not looking at the crystal. It's actually hitting this knob. So what I'm going to do is I'm going to tilt the collimator so that the beam goes straight back. So I'm tilting it sideways. Now the beam is right below the crystal, and now it's going through the crystal. Okay, so now this is looking at the crystal, and the beam spot. Well, let me see. I can move this thing a little bit. It is close enough, I think. All right, so let me verify. Okay, I got as far as I can go by holding a mirror with 2 fingers. So, and this is just a cheap mirror. Okay, so then this screw alignment is good enough to let light go through this fiber. So I'm not gonna remove this. Well, let me put it right here. Put my glasses here. Fibers have a notch, and that notch has to align with another notch in the collimator, and then that way it goes in up to the right position. It's also important at this point to check that all our knobs are tight, because if they're not tight and if we move the collimator, we have to start all over. Okay, so you can see there that light is coming out of the fiber. So then we could do some extra alignment. It is a multi-mode fiber, so the light bounces in every which way through the fiber. So what comes out is not a nice round, clean beam. It is an interference pattern produced by the light bouncing in all possible directions through the fiber. There's actually a lot of very interesting optics to do with that. And so what we do is we align so that the beam comes out as collimated as possible. And now this collimator and fiber are ready to go. Okay, so I just finished aligning the second collimator. The other thing, the alignment laser is off. The other thing that I did is to connect the fiber laser to the detector. And then the detector, which is not yet powered, has an output which will produce square pulses for each photon that comes in. through the fiber, and then that gets connected to the computer. And before I get to the computer, let me finish here. So as far as this setup is concerned, we're ready to go. And then the next thing we will do, one last thing, is to put a filter on in front of that fiber. This is my own preference. Others do something different, which is actually quite convenient, but I just don't do it. And that is, between this and the detector, they put a filter. They put the filter there. So then there, for the extra inconvenient of doing that, you get other things are convenient. For example, right now the ambient light can go into the fiber, and then the detectors are going to register those as photons. In fact, this amount of light is too much, way too much. So we need to cut it down. And if we don't put filters, we actually have to cut it down to almost absolute darkness. Now, what we can do to get to avoid the background light to get the detector, those are unnecessary photons, is we eliminate all the infrared photons. So what we do is we put band pass filters. These are 40 nanometers, centered about 800 or 810 nanometers. These particular ones are centered around 800. So I just put them there. So now only a small fraction of the light is hitting the detectors. It's only the light that goes through those filters. But still, there's a lot of photons in that range. So for that, we need to turn the lights off. And in the other method, the filters are already incorporated, so there's one doesn't have to be too worried about placing these filters in front. Okay, again, it's not a huge advantage, but it is convenient. Okay, so the next step would be to turn off the lights and turn the laser on, and then start looking for counts. Another thing that we need to do, I had it here, is to provide a beam dump for the blue laser, because most of the blue laser just goes through, and that blue laser is actually quite powerful. So we're going to dump it into this beam dump. All right, once the lights are off, and if we don't see any counts, photon counts, various things can happen. The first one is that these are not optimized, but we already optimized them with the alignment lasers. So I would say these ones are very close. So probably if we don't see any photons, that is not actually the right culprit. The crystal, we just aligned the crystal crudely so that the beam gets reflected on the front surface. So that alignment is very critical. So it could well be that the crystal is just not at the right place. So now, this beam is, the beam of the blue laser is horizontally polarized. So then this crystal here has an axis in the horizontal plane, an optic axis in the horizontal plane, and what we need to do is tilt it in this direction. So what we would do, and what we will do, is to turn off the lights, turn the laser on, then see what we have. And if what we have is not what we want, that we just lots of counts, then the first place to go to improve that is to tilt this crystal in this horizontal plane. And once I've done that, I would still do some fine-tuning of these four. And at that point, we should be getting down-converted photons. And we can do experiments. Now, on the electronic side, what do we have here? We have a computer, and the computer right now is, in this particular case, is connected to an FPGA Altera board that takes up to 4 sets of inputs. In this case, I only have 2. And this was that particular board, and the programming of that board was developed by Mark Beck. And you can find information about it in his website. But I'm aware that there's others that have a similar system. At NIST, they have also an FPGA system that does the same thing. And now, inside the computer, then we have a LabVIEW program that knows how to talk to the board. So the board is receiving pulses, and then LabVIEW is just going to graph them in some way that is convenient to us. Now, that's all we need. And in principle, for just getting down conversions, we only need Altera board, a computer, and everything else. If we want to do more things, for example, an interferometer, and I'm going to have another video explaining how to align the interferometer. And for doing interferometer, we have to scan something. In that case would be the path length of the interferometer. So then the computer needs to send signals out to something that scans or steps a scanning process. And for that, we need a digital to analog converter. So in that case, we need more than just the Altera board. But for what we're going to do today, that will be enough. Okay, so the lights are out. We do have green LEDs, and then these are very narrow band, so that the green photons are not going to go in through the filters. So the detectors are going to be detecting only infrared photons in the bandpass, in their bandpass range. We also have the laser on, and you can see it here. This is a $20 laser pointer, blue laser pointer. But don't be fooled. It's very powerful. It's actually about 50 milliwatts, and so beware of certain laser pointers that they say that they are low power, but they're not. Also, another thing about certain lasers of these kind is that they also produce infrared. So in certain cases, not this one, we have to worry about that. But anyway, so the beam is coming here, stirring the corner, now hitting the crystal. And then after the crystal, the beam, you can see, goes almost unchanged and into our beam dump. The detectors are on, and right now we do have down-converted photons coming out in all directions and at all different wavelengths. But then we are going to be looking at one particular subset of those photons, those that are coming at the same wavelength and coming out at plus or minus 3 degrees and in the horizontal plane, because they come out in a cone. And of course, we can't see anything because they're both infrared and the light is too weak for us to see. Okay, so then here we have a LabVIEW program that has a number of screens here, and these screens display I think at the very top they display the raw photons that come in from the detectors. And the Altera board has a possibility of us to do certain operations with them, like coincidences. So this frame here is going to display the coincidences. And so then when I start this program, what it's going to do is it's just going to record the number of counts from the two detectors, which will appear in these two frames, and also will graph as a function of time the coincidences. And what we've done is we've set it up so that every second we display an update of the counts that are recorded in 1 second. So let me get this started. And there we go. So we have some counts here. I'm reading about 5,000 here and here. It is possible that this is some light leaking in. We have some background light right now. And who knows if all those red photons are finding their way in there. Now let me block one of the beams. Let's see, if I block completely, this actually goes down. So there are some light that's being recorded here. But now it goes down only to 2,000 counts. And so then the remainder of the counts are either background counts in the detector, or they are light that still manages to leak in through the fiber and into the detectors. And something similar happens with the other side. So if I block that side, also the signal goes down. Okay. All right. So again, so we see all these signals, and then we look at the coincidences, and we have coincidences that are the range of 1, 2, not very promising. Let's try another thing. Let's block the laser beam. So I'm putting my card on the laser beam, and so then the light actually does go down. And those coincidences are also going down. So we're getting some down conversions. But 1 to 2 or 3 counts is hardly what we want. So what is going on? Like I said before, the primary culprit could be the crystal. So what I'm going to do is I'm going to tilt the crystal and then look at the counts in both of them and in the coincidences. And if we're off by just a couple of degrees, we're going to the counts that we get are going to change by a lot. So so I'm going to start tilting the crystal. So now I'm going to start tilting the crystal, and so then you want to look at the screen. And then all of a sudden, you start to see that the counts are going up. As I'm still turning in the same direction, so actually we're quite lucky. We are getting a fair number of counts. So I'm going to keep going until it stops rising. Now, the the other place to look at is the coincidences. So when the coincidences start to go down, that means we passed the sweet spot. In fact, that's what we're seeing right now. And now I just on purpose went past the sweet spot, and you can see both the singles and the coincidence are going down. So I'm going to backtrack and then settle for a healthy set of coincidences and singles. Probably that is a good spot. So then now we have about 25,000 on each channel for singles, and then coincidences we have about 60. And now if I block one of the beams, the coincidences go down to single digits, and the same thing will happen if I now block the other side. The coincidences go down. And there's a way to calculate which of these coincidences, how many of these coincidences are accidental. My estimate is that those are in the single digits, maybe 3, 4. I haven't done the calculation for these counts. To get them, you multiply each of the singles times the time window in which we're recording coincidences. And that is going to give you the number of accidental coincidences. And I'm, again, just from past experience, those are for these level of counts, we're in the single digits. And right now we're recording about 60, so is a few accidentals out of 60. That's pretty healthy. So at this point, we can start doing things, but this is not the last word. We can get much more. In fact, an optimal amount of coincidences is about 10% of the singles. So I haven't aligned touched the collimators. As soon as I start tilting them, I could optimize those. Those will go up as well. And also, if for some reason, when I'm looking at coincidences, the coincidences are going up and the singles of either channel, one going up and the other one is going down, that means that the collimators are not in the right place, so that we're not detecting all of the partners. We are detecting some partners that on the other side, some photons that on the other side, the partner is not being detected. So that's another thing to look at. But for now, this is good enough. We can do now quantum experiments. Thank you.